Today we're going to explore key concepts in cloud computing, including deployment models, virtualization, software-defined networking, storage, network and compute security controls, and cloud security solutions. These topics are essential for understanding how modern IT infrastructures operate and how to secure them effectively. Let's start by looking at cloud computing and deployment models. Cloud computing is a model where IT resources are provided on demand over the internet by a cloud service provider. One example is Microsoft, which offers Azure as cloud computing service. There are three primary cloud computing models. First, infrastructure as a service, or IaaS, provides on-demand infrastructure components like networking, storage, servers, and virtualization. An example is the Google Compute Engine, which is the IaaS component of Google Cloud Platform. Second, Platform as a Service, or PaaS, delivers hardware and software tools for application development and deployment, including networking, storage, servers, virtualization, operating systems, middleware, and runtime components. Thirdly, software as a service, or SaaS, offers software applications over the internet with the provider managing access, security, availability, and performance. Gmail, provided by Google, is an example of an SaaS email service. Additionally, the term anything as a service, or XaaS, refers to products, tools, and technologies offered as a service over the internet, such as communications as a service, which might include voice over IP and video conferencing services. Cloud deployment models define the architecture, scalability, ownership, and control of cloud services, as well as how they're made available to users. There are four types. A public cloud is provisioned for general public use, hosted on the cloud's provider premises and accessible over the internet. It is often deployed as a pay-per-use service. Examples include Amazon Web Services, Google Cloud Platform, and Microsoft Azure. A private cloud is dedicated to a single organization. It is managed either by the organization or a third party and can be on-premises or off-premises. A virtual private cloud is a private cloud embedded within a public cloud. A hybrid cloud combines private and public clouds using standardized or proprietary technologies to share data and applications, such as storing sensitive data on a private cloud and a business intelligence application on a public cloud. A community cloud serves organizations with shared computing concerns like regulatory compliance or security requirements. It can be managed by the community or a managed service provider located on or off premises. Now let's look at fog and edge computing. Fog computing is decentralized infrastructure that extends the cloud by placing nodes between the cloud and end devices. A fog node, which has computing, storage, and network connectivity, processes data near end devices to reduce cloud latency. This enables near real-time decision-making while sending data to the cloud for storage and long-term analytics. Edge computing processes most data at end devices. This minimizes data transmission to nodes or the cloud, which improves responsiveness and reduces bandwidth usage while lowering latency. In manufacturing, for instance, edge computing uses sensors for real-time analytics to enhance product quality. A self-driving car, for example, might use edge computing for onboard navigation, fog nodes for low latency data exchange with nearby cars, and cloud computing for long-term analytics like maintenance tracking. Next, let's look at cloud regions and availability zones. A cloud resource is a physical device in a cloud provider's data center. A cloud resource is a physical device. A region is a cluster of data centers, and an availability zone is a smaller group within a region. Region isolation provides service stability by eliminating single points of failure. Regions are physical locations of clustered data centers such as Amazon Web Services spanning over 20 regions across North America, South America, Europe, China, Asia Pacific, South Africa, and the Middle East. Availability zones are smaller groups of data centers within a region, such as AWS's over 80 zones, including Ohio, Rio de Janeiro, Cape Town, London, Bahrain, and Beijing. Regions vary in performance, cost, and latency and are isolated for fault tolerance and stability. Availability zones within regions enhance redundancy and connectivity for disaster recovery. Now let's look at multi-cloud systems. A multi-cloud system integrates services from multiple providers to optimize performance, reliability, and cost effectiveness. It helps avoid vendor lock-in and enhances disaster recovery. It also tailors workload deployments to each provider's strengths, increasing resilience against outages and disruptions. Next, let's look at containers, serverless, and microservice architectures. A container is a software package with all elements needed to run an application, including code, libraries, system tools, and configurations. It is decoupled from underlying hardware, allowing it to run on virtual machines, physical servers, on-premise data centers, or public clouds. A container engine like Docker, for example, manages container execution, virtualizing the operating system rather than the hardware. This makes containers lightweight and efficient compared to virtual machines, which require booting an OS and loading libraries. Containers are OS specific, so a Windows containerized application runs only on Windows. Containers resolve issues like running a Python application with an older interpreter by including the required version or enabling a legacy C application by packaging its old libraries. They run faster than virtual machines because they avoid hardware emulation. Serverless architecture automatically provisions and scales resources. The cloud provider manages provisioning, scheduling, and scaling. Microservice architecture breaks applications into smaller, independently deployable components with their own technology stacks and databases communicating via APIs. This supports continuous integration and deployment, often within containers for real-time applications like traffic control or e-banking. In serverless architecture, the provider scales resources. Monolithic applications are built as single units, while microservices operate as independent services. This allows for updates without disrupting the entire application. Platform diversity involves deploying application components across environments like containers for scalability. This also improves efficiency and reduces vulnerabilities. Now let's look at virtualization. Virtualization uses software to simulate physical computing resources. This forms the basis of cloud computing by creating virtual machines for efficient hardware use. A virtual machine consists of a hypervisor which virtualizes the host machine's hardware. Two types of hypervisors exist. A Type 1 or bare metal hypervisor runs directly on the host. It interacts with physical resources without an operating system and typically utilizes powerful servers. A Type 2 or hosted hypervisor runs on an existing operating system, using it to access hardware. Virtualization faces traditional exploits, such as malware. Resource reuse refers to sharing memory or I/O devices. It risks a compromised VM accessing others' resources if isolation fails. Mitigation includes patch management for both host and guest machines, updating the hypervisor, and virtual machine lifecycle management. Now let's look at software-defined networking. Infrastructure as code, or IAC, manages data centers via machine-readable definition files instead of hardware configuration. It uses scripts or declarative definitions to set a desired operating state. Unlike traditional step-by-step configuration, IAC pushes definition files to providers for automatic resource assignment. This manages physical resources like virtual servers with desired state declarations. One type of IAC example is an overlay network. It is a virtual layer atop physical infrastructure, enhancing performance without new equipment. A software-defined networking, or SDN, centralizes management and control planes for traffic management and resource allocation. It also adapts to network changes. A software-defined wide area network, or SDWAN, extends SDN to multi-location networks. It embeds security like encryption and firewalls for consistent policy enforcement. The control plane directs packet transmission, and the data plane transmits packets while the management plane oversees nodes. SDN streamlines management, while SDWAN centralizes multi-location networks. Software-defined visibility, or SDV, enables traffic monitoring across cloud and on-premise networks, regardless of device location. Cloud applications use APIs for integration, and SDV inspects API calls to SDN components. It assesses vulnerabilities and ensures best practices. SDV provides seamless visibility into all traffic, local, internet, and cloud. It allows effective policy application, unlike non-SDV setups which require multiple and efficient solutions. Now let's look at storage, network, and compute security controls. A virtual CPU allocates a host CPU portion. Virtual RAM provides memory. Virtual networking offers network access, and cloud storage manages data. Dynamic resource allocation automatically provisions and deprovisions resources based on demand. It also enhances scalability and cost efficiency. Cloud providers ensure high availability across zones with high bandwidth, low latency, and redundant links. Physical separation aids disaster recovery against natural or man-made incidents. Resources like virtual machines have resource policies defining authorized users and actions. Hardware security modules store certificates, keys, and passwords for secure data management. Auditing evaluates security controls and compliance. Security groups act as virtual firewalls, associating users with policies like blocking TCP port 23, for example. Instance awareness recognizes multiple service instances for policy application. Virtual networks use controls like physical networks, including virtual firewalls and segmentation into subnetworks for access control. A VPC endpoint connects to VPC instances without public IPs, and a transit gateway links on-premises networks to VPCs, acting as a scalable virtual router. Together they form a private direct connection, often with VPN add-ons for encryption. A cloud responsibility matrix clarifies roles between providers and customers. In Internet as a Service application, providers manage physical infrastructure while customers handle OS, applications, and data. Cloud vulnerabilities include resource misconfiguration, insecure IPs, and shared technology risks like hypervisor flaws, risking isolation failures. Robust measures mitigate these risks. These may include audits, penetration testing, incident response, API security, and access controls like multi-factor authentication. Now let's look at cloud security solutions. A Cloud Access Security Broker, or CASB, enforces security policies between an organization's infrastructure and cloud services. It is deployable on premises or in the cloud and handles authentication, authorization, encryption, logging, alerting, and malware detection. A CASB offers visibility into usage, ensures compliance, secures data by accessing parameters, and protects against threats. A secure web gateway, or SWG, protects against web threats and enforces use policies at the application layer. It utilizes URL filtering, malware detection, and data loss prevention. A next-generation firewall, or NGFW, provides advanced capabilities like intrusion prevention and application control. It segments networks into trusted and untrusted zones. Firewall as a Service, or FWaaS, delivers NGFW features in the cloud. They filter traffic to prevent unauthorized access. Cloud-native security builds protection into assets across an operating system, including the container and the application layers, dissolving traditional parameters. Controls include visibility and audits for compliance, high availability via server clusters, DevOps integration with microservices and IAC, and mitigation for data, network, and compute resources. One example for reference is using HTTPS for two-factor authentication. Secure Access Service Edge, or SASE, combines WANs and security services into a cloud model. It is used for supporting secure web gateways, firewall as a service, cloud access security brokers, DNS security, and data loss prevention. It includes zero trust network access for secure application access managed from one platform to better enhance control and security.